This show has too much in it, and it takes impossibly long, and I know that. Um, when we get to 30 minutes, I'm going to tell you to stop watching. I'll continue recording in case you are watching this because you missed class and need to have the information that we go over in class, but let's go. So if these power lines have little signs on the bottom says danger, high voltage, but if it's dangerous, then why do it? And that's the hook for today. So, will you please recall the definition of power? Stop the show, write it into this box, then you start the show again, and if you did not write the rate of working, then write that in the second box. So, as regards the rate of working, what electrical measurement involves work? Again, stop the show, you start it again, and if you did not write in the first box this rate, the work per charge moved with the awkward negative, then write it now. So these look very similar. If I could just get rid of that T and replace it with a Q, or vice versa, I could have the identical formulas. So Q and T, what electrical measurement do you have that involves charge and time? You stop the show, start the show again, and I'm sure that this is what you wrote. If you didn't, you put that into the box. And then you can see that it follows from the definition of voltage and current that if you multiply voltage times current, you will get power with this issue of the awkward negative, which we are not going to deal with. Power is the rate of working, but frequently you will have a problem that asks you about the energy dissipated or the energy transformed, and that energy transformed, the work, could be found by multiplying time times power, which means power, which is in watts, times seconds. A watt second is a unit of energy. Indeed it is. It is such a small unit of energy that it doesn't fit for the way you consume electrical energy, and so every month your parents pay for thousands of watt hours. Kilowatt hours is the way you pay. You pay about 9 or 10 cents a kilowatt hour for the energy that you consume during the month. The power company doesn't care about how quickly or slowly you consume the energy. They just consider how much energy you consumed. You could write Ohm's law. Now you started the show again, and you have Ohm's law, which of course only applies to ohmic devices. But if it were an ohmic device, then you could replace V by IR, and we have another expression for power. It is the current squared times the resistance. This is true for all things. This is only true for ohmic things. And you could replace I by V over R, and you get this expression for power. They're useful to have. So here is a problem for you to do with those ideas. Do it. Here is another set of problems for you to do. Please do them. Please notice this is in minutes. If you're going to get an answer in joules, you're going to have to change that to seconds. And finally, this problem. Now, I want to talk about why we transport at high voltage, and this is what takes so long. We need to distinguish between the transport of the energy from the power company to the consumer here in the big city and the voltage drop there in the city, that is the consuming of that electrical energy. This power here is going to be equivalent to the potential difference between the two ends of the wire times the current that's flowing there. And similarly, this power that happens here is going to be equal to the potential difference between two wires, not between the ends of the wires, that was for transport, but between one wire and the next wire. The current flows out from the power company through our devices in the city and then back to the power company. There's the complete circuit. It will be the same current flowing here as flowing here, so it is the same I. This power loss is just the wires dumping heat into the air, and nobody pays the power company for that. And so the economy comes by making the current as small as possible. I would like to make the resistance as small as possible. I make the wires fat, but I'm stuck with the distance between where I made the power and when I'm using it. So I make the resistance as small as I can, but then if I make the current small, then I end up with less power being lost as the square of how much smaller I made the current. If I make the current a tenth as big, then I'm dropping a hundredth as much power. But if I just make the current smaller, then that's going to impact the power that the city needs. And the city needs something on the order of 1,000,000 megawatts. Not 1,000,000 megawatts, a megawatt. 1,000,000 watts, 1,000,000 joules of energy every second. Electrical energy being transformed into some other form of energy. Well, if you've made the current smaller to get economy here, then you're going to have to make the voltage proportionally bigger. If I made the current, say, 10 amps flowing here, then I would have to make the voltage 100,000 volts in order to get a megawatt to the city. And that's why we transport at high voltage, so that we can transport at low current, so we can minimize the power loss during transport. Now, 100,000 volts between these wires and 100,000 volts between this wire and the ground means that there's the potential of arcing, of a spark jumping between those two because of the large potential difference. That makes for a very strong electric field. Well, that's why we run these wires high. That's why we run these wires relatively far apart. And that's why we're limited. In Virginia, we run at about 500,000 volts across the countryside. In out west, they do it at 700,000 volts, but there's a limit. You can't do more than that, or you'll start to get this arcing between the wires and between the wires and things in the environment. So we push it as high a voltage as we can, because that means we're going as low as current as we can. That reduces the power loss here. But that means that when you get to the city, you cannot deliver hundreds of thousands of volts into people's homes. It's not, you get arcing here, you're going to get arcing in the home. It's going to be a hazard. And so we use transformers. We take it from hundreds of thousands of volts down to tens of thousands of volts, because we still have a distance to go from these transformer stations to your home. We're going to, instead of sending it along these wires way up high, we're going to be sending it along these wires beside the roadway, and we want to keep the current low, and so we want to keep the voltage high. This time it's more like tens of thousands of volts, and we do that through several transformers. And then finally at your home we have a final transformer which brings it from, say, 10,000 volts down to the 100, 200, actually 110, 220 we usually say, volts that you use inside your house. Between this wire and that wire would be 110. Between that wire and that wire would be 110. Between the outer two wires is 220. This is what it looks like where I live, where the power lines come in above ground. Where you live, probably power lines are underground, and so the transformers are out in some one of your neighbor's yards. You go up close, you can hear it humming, and that is bringing the voltage down from about 10,000 volts to 110, 220 that you're going to use in your house. Analogies. When we talk about electrical voltage, we need analogies because we can't understand it. And so we talked about potential difference for voltage, meaning it's like potential energy that is there because of the difference. But it's not energy, it's voltage. We also talked about EMF, that it's like a force. Voltage is like a force that makes electrons move. Yes, it is, but it's not a force. That is an analogy for voltage. Now we're going to talk about electric circuits, and the analogy that is typically used is a plumbing system full of water. But because I'm not sure that you appreciate how incompressible water is, I am instead going to talk about marbles in a tube. When a current, this is an electron, when it goes through a wire, it is not one marble traveling through an empty tube, but instead it is a tube that is full of marbles. And for one electron to go into the tube means that all of the electrons in the tube have to move over, and one marble has to come off the other end. This leads to your understanding of an electric circuit. I'm going to have to back you up, back up, back this up. There you go. That in order, this notion that you can't put one in unless one can get off the other end is why you need a complete circuit for current to flow. If it is not a complete circuit with a place where you put electrons into the wire and a place where you take electrons off the wire, if you do not have that complete circuit, no current flows. And if you have a switch in the circuit and the switch is open, no current flows anywhere. When you close that switch so that electrons can move here, then they suddenly move everywhere. Why? Marbles in a tube. They flow the same everywhere. Let's see if this says everything. It's full of electrons. And for one to enter, they almost move over, and so it is the same current everywhere. And for one to get on, the last one has to get off. You have to have a complete circuit. Now, let's consider an electron whose name is Ellie. And this is Ellie's first time to go through a circuit. I'm going to pretend like it's an empty tube, just for the sake of my discussion now. And Ellie starts off with 3 volts. Remember, the current flows from high to low, but that means the electrons are going from low to high. So here is Ellie the electron feeling very repulsed by this negative and very attracted to that low potential. And so Ellie sets off and starts traveling around the circuit and comes up to this, which represents a difficult place to get through, a resistance. And that's the place, because it is difficult, that's the place where the electrons do work. And Ellie knows that, oh, this is the place where I'm supposed to drop voltage. There's supposed to be a potential difference between this side and this side. And so Ellie drops all 3 volts across here, and then carries on merrily with her trip around the circuit and comes up to this resistor, and she is shocked. Haha, shocked. Oh my, she says, if I'd known that you were here, I would have saved some voltage to drop across ye. But that's not the way it happens, because this tube is a tube full of marbles. And when Ellie comes up to the first difficult place, she knows that the second difficult place is there. If it's hard for the marbles to get through here and hard for the marbles to get through here, Ellie knows it before she even gets there. Why? Marbles in a tube. She knows it's hard to go forward, someplace up ahead, because these marbles are having trouble getting through, and this marble is having trouble getting through. It's like traveling in a traffic jam where it's bumper-to-bumper traffic, and you know there's an accident up ahead because you can't move forward until the car in front of you moves forward, and this car is having trouble getting around that accident. And even when you get around that accident, you know that there's another one, because everybody back here is having trouble if these people are having trouble. Before we go on, I want to acquaint you with the fact that the actual movement of electrons in a wire is on the order of millimeters per second. They are crawling through the tube. But the fact that they're moving is communicated at about 1/10 the speed of light, very fast, that this end of the wire, if you close this switch, then the electrons start moving here almost instantly. Why? Because if they can move here, then they can move everywhere. It's going to be marbles in a tube, and that fact of motion gets moved through the wire very fast. Okay, now your task is to go through these circuits and label them with a P or an S. You stopped the show, you started the show again, and I hope you labeled this one with a P, looks parallel, this one with an S, it looks series. This one is a little more tricky, but it should have been labeled with an S. This one should have been labeled with a P, and this one is neither. It shouldn't have been labeled. It's what we call a mixed circuit. Okay, that the idea for a series is that you go through one and then you go through the next one. Whereas for parallel, you go through one or you go through the next one. That this is the high potential side of the seat of EMF. There's the low potential side. So this is the high potential side of that resistor. There's its low potential side. Here's the high potential side of this resistor. There's the low potential side. And once the current has chosen to go through this resistor, it's not going to then go through that one also, because current doesn't flow from low to high. So once it's gotten through that resistor or this resistor or this resistor, it doesn't go through any more resistors. It goes back to the low potential side of the seat of EMF. So it goes through one or the other. That series means they're one after the other. Parallel means it's one or the other. Okay, in the spirit of analogy, I have built a model of the James River in my backyard, but it's actually a model of this electrical circuit. It has a pump, seat of EMF, that raises the potential up, and then it has these difficult places to get through. That's where the potential gets dropped. That's where the water falls. The one last detail to make this be a good analogy is that I have to put plexiglass right at the surface of the water everywhere here, so that if I put a dam in and stop the water moving here, it needs to stop moving everywhere. It shouldn't have the option of going up higher behind the dam like real water would. Then this becomes a good analogy for this electrical circuit. Now, if you go to my model in the yard, and I find that across this waterfall it drops 2 meters, and across this waterfall it drops 3 meters, how much would it drop across those two together? Alternatively, if you went by this channel, how much would it drop across that waterfall if it drops 2 here and 3 there? And the answer is 5 meters. That when you have resistors in series, if you drop 2 volts here and 3 volts here, then the equivalent resistance across the two of them is that you will have dropped by 5 volts. And if you go by this alternate route, this parallel route, you're going to drop 5 volts there. That between that spot and that spot, there is a difference of 5 volts, whether you go this way or that way. In the same way that between this spot and this spot, there is a height difference, a difference in gravitational potential of 5 meters. It doesn't matter whether you go that way or that way. It is going to be 5 meters. Now, suppose that 200 gallons per minute were flowing through that resistor. Well, how much water would be flowing here? How much water would be flowing across that waterfall? And the answer is that across all of them, all of those places, it would be 200 gallons per minute that would be flowing. Suppose there were 100 gallons per minute flowing across this waterfall. Well, then how much water would be flowing there? How much water would be flowing there? And the answer is, come on now, that both at this junction at the top and at the junction at the bottom, there would be 300 gallons flowing here and 300 gallons flowing there. In the same way that if there were 2 amps flowing here and 2 amps flowing there, and there was 1 amp flowing here, then it would have to be that there were 3 amps coming in, splitting up, and here where they came together again, the 2 and the 1 amp, it would be 3 amps coming out. That when you have resistors in series, the voltages add to the total voltage and the currents are the same. When you have things in parallel, the voltages across them are the same and the currents add. And at a junction, the sum of the currents into the junction is equal to the sum of the currents out. You can try your hand at this task here, where you have 5 in and 9 in and 4 out and 3 out. What's going on in that one? What direction and how much? Resistors in parallel, in series. And what I want to do is to think about what is the equivalent current, what is the equivalent voltage. That is, I'm going to replace these 3 in series by one resistor called the equivalent resistance. And what is true about the currents through all of those? Well, of course, you know that the currents are everywhere the same. What is true about the voltages for those? The voltages add up to the equivalent voltage. So, using Ohm's law, V is equal to IR for each of these. But the I is the same, and so we get that the equivalent resistance is equal to the sum of the individual resistances. It is a consequence of the fact that resistors in series have the same current and that the voltages add to the equivalent voltage drop, that the equivalent resistance would be the sum of the individual resistances. Try your hand at this problem. What is the equivalent resistance? Here we have resistors in parallel. So what is true about the voltages for those? They're all the same, and they're all the same. If I were to replace this by one resistor called the equivalent resistor, it would be the same. What is true for the currents? The currents through each of those individual ones add up to the equivalent current going through all 3 of them. Then I replace each of the I's by V over R using Ohm's law, and we have that the dividing out the equal V's, I have that the reciprocal of the equivalent resistance equal the sum of the reciprocals of the individual resistances. Again, a consequence of how voltage and current behaves for parallel. Here you go. Try your hand at it. You can't be lazy. Go ahead and take the reciprocal of 4, reciprocal of 6, reciprocal of 12. You could find a common denominator, or you could use your calculator to find the reciprocals. But when you're done and add up the reciprocals, don't forget, you need to take the reciprocal of that to get what the equivalent resistance is. And I think you will find that it is smaller than any of these. That is very important. For resistors in parallel, the equivalent resistance is always less than any one of the individual resistances. Here's a mixed circuit. What you do with a mixed circuit is to either mentally or with a pencil, you need to put a box around the part that is pure. This is pure parallel. And then I'll put a lid on top of the box so that I can't see that confusion inside. And now what I have is this resistor in series with the box and its equivalent resistance. That's the way you deal with it. Now, here I had 6 and 3 in parallel, so that's 1/6 and 1/3, and I think you'll find that that adds up to 1/6 and 2/6 is 3/6, that's 1/2. The reciprocal of that is 2. So what these represented was 4 ohms followed by 2 ohms, so the equivalent resistance there is 6. You try your hand at it. This is just parallel. It's not a mixed circuit. And this one here, so rich, so rich. We're going to do these again and again until you get good at them. Probably you will have a little bit of a struggle here, but do it in the order I suggest the problems to you. So based on IB, what is IA? Oh, there's IB. How are they related? What do you know about the currents there? And then we'll go on to IB, IA, and ID, and from that we're going to get to IC. Let me point out to you, for fear it is not evident, that this is the high potential side, so the current flows from high to low. That makes this the high potential side, and so the current is going to flow from high to low in this direction. And so here too, the current must flow from high to low, and here it flows from high to low, and thus we can get the currents flowing into this junction and the currents flowing out of that junction, and we can get IC, and we can also get to IE by the fact that there's 5 amps flowing into this junction, how much is coming out. Another mixed circuit which you are to take apart and find the equivalent resistance of. And this problem, again, a mixed circuit, find the equivalent resistance. And we're probably out of time at this point, but so stop watching the show if indeed it says to do that on your worksheet. I'm going to go ahead, but we will go over all of this in class. You do not need to watch it. Here is a toaster. Here is the filament of the toaster. This is a real toaster, and so the wires from the wall to the toaster do have resistance, and I've represented the resistance which is distributed all along those wires, all at this place here. So we're dropping 100 volts across 1,000 ohms, which means that we will have a tenth of an amp flowing through this resistor, and a tenth of an amp flowing through the filament of the resistor. We're dropping a tenth of a volt across that resistor. We're dropping 99.9 volts across here, dropping a total of 100. And here we are have a power of 100th of a watt, which means every second this 100th of a joule of heat is generated at the expense of electricity here in these wires. They do warm up, but they quickly get sufficiently above the temperature of the air around them, that they are radiating heat into the air at the same rate they're warming up, and then they don't get any hotter. The toaster, however, has about 10 watts, and that means that every second it's changing 10 joules of electricity into heat. That's 1,000 times. Yes, 1,000 times as much heat, and that's where the heat to toast my toast comes from. At least it was until I stuck some cinnamon toast in there and it got stuck down in the toaster. So I reached into the drawer and pulled out a knife, and I dug down in the toaster to try to dig that toast out, and accidentally my knife made electrical contact across here. And that was a bad moment, because these two being in parallel means the equivalent resistance is going to be less than the resistance of either one, and this, being a good silver knife, had equivalently zero resistance. And so all of the current starts flowing through the knife. The equivalent resistance here is 0 ohms, and so suddenly we are dropping 100 volts only across this 1 ohm. Suddenly all 100 amps, we're dropping 100 volts times 1/10 of an amp, times across 1 ohm, so we have 100 amps, 1,000 times as much amps, which means 1,000 times as much voltage, potential difference. We're dropping a whole 100 volts across here, which means the power is 10,000 watts. 1,000,000 times as much heat is being generated every second. It is catastrophic. This is what's known as a short circuit or a shorted circuit. There is too little resistance. Instead of 1,000 ohms of resistance to drop 100 volts, we're dropping 100 volts across 1 ohm. Too much current. There's this explosive overheating, which in fact will destroy either the knife or the wire, probably both. And so there'll be a little hole in this wire, which means the current stops flowing. There's this one explosive event, as long as you are not blinded or burned by that, and there's nothing explosive in the air that causes an explosion in the room, that momentary flash of spark as this wire vaporizes will be the end of it, and no current will flow after that. A much worse event is this one, where I'm plugging many appliances into the same circuit. I apply a 100-watt refrigerator in, it's dropping 100 volts, which means 10 amps is flowing through the refrigerator. That's fine. That's how the refrigerator was designed. But I also plug a 1,000-watt microwave into the same circuit, which also draws 10 amps, which is fine, but this wire, which was carrying 10 amps, and it was fine with the 10 amps, is now carrying 20 amps. And that means 4 times the power being dissipated here. I plug in a blender into the same circuit. It draws 10 amps, which means now you have 30, which means you have 9 times as much heating as when you had 10 amps flowing there. And finally the waffle iron, which coincidentally draws 10 amps. So now you're drawing 40 amps here, and this causes these wires are probably doing okay, but these wires here get very, very hot. That's back inside the walls of your kitchen, and you're not aware of it, and that causes your house to catch fire. This is called an overload, and it's a result of too many parallel circuits going, each of these being in the same circuit. They're all parallel, which again causes too much current, just like with a short circuit. But this time, instead of explosive overheating, it causes this insidious overheating. And I found out that a lot of people don't know what insidious means. This gradual, subtle overheating, which you're not aware that anything bad has happened, but inside the walls of your house there is this heat that is building up until your house catches fire. The protection against overloads is, one, in your kitchen, the refrigerator's on a circuit all by itself. And then along the countertop, there are multiple circuits. So when you plug the microwave and the blender in, they're probably not in the same circuit. And that is the way we protect against the overload. The other protection is to put a weak link into the circuit. It's called a fuse. The word fuse means melt. Fusion is melting. And we put a fuse in there, so when all these wires are getting hot, this is getting hot too, and it's designed to melt, to fuse, when the temperature reaches the rating of that, and that then makes an opening in the circuit and no current flows. Here are pictures of fuses. This is an alternative to a fuse called a circuit breaker. That's what the inside of a circuit breaker looks like. Here's a breaker panel. I'll talk about those in class.